We are still finishing solving the equations of motion. Step 1 is building our idealization, the model. Step 2, constructing the equations of motion. And we have two ways. You either use the Newtonian force approach or you use the Lagrange work energy approach. And 3, solving the equations of motion. Today we're going to go through solving the equations of motion. Solving the equations of motion, we have two ways. The first one is the initial value problem, where I will give you initial velocity and position and the equations of motion, and then you solve for the trajectory and the time. For the boundary value problem, which is the second way how do we solve the equations of motion, I will give the initial configuration, the final configuration, and the time between to move from that location to the other location, and then the solution will be the trajectories and the initial velocity and final velocity. This is the entire model of how do we do human motion analysis. Idealization, formulating the equations of motion, and then we do the solution of the equations of motion. If we want to generalize it in a matrix format, we will say that mass times acceleration equals force, right? V dot is the acceleration, the velocity derivative. And the mass is a generalized mass matrix. You remember the relation matrix? It's a combination of the relation matrix and the diagonal mass matrix. And then you will have the force as a function of position and velocity. The mass is a function of position. X is only position. So this big M here is actually a relation matrix transpose with a diagonal M matrix, MD, and then we have the relation matrix not transpose. The transpose is moving the columns to be rows and the rows to be columns. The relation matrix, we get it from the idealization, how the segments are connected and where are the masses and the lengths. The diagonal mass matrix, so let's say if you have 3 masses, right? So you'll have M1 and then 0, 0, then 0, M2. You'll have the masses on the diagonal, and then you have 0, 0, M3. That's your generalized mass matrix, the M double star here. And this all of them are lengths, L and Z, and the mass is constant. It's not changing. It's not going to change. Okay, so if you have this set, and the V dot, X dot is equal velocity, the derivative position is velocity. Remember, this is constructing the equations of motion. You can, I don't want to make one by one each equation separately, but I can build a matrix and have all of them together. So you can generalize the formation of this by having A X equals B, right? So this is A, that's a matrix. X is an unknown, equals B. And if you remember your linear algebra, we can solve this system, right? So the thing that we solve for all the time is X dot, which is velocity, and V dot, that's acceleration, right? And solving this, the easiest thing to do is just to have it multiplied by A inverse on each side, right? A inverse multiplied by A is the identity matrix, so I will have the X equals A inverse multiplied by B. And that's the easiest way to solve a system of equations if you are having them written in a matrix format. That's the easiest way to do it. Now, the AX is this one, that's A, that's B, and that's the unknown X, the thing that we would like to solve for all the time. That's what we want to solve for. Now, B, it has velocity, right? And it has, so F is a function of position and velocity, and V is V. So if I gave you V at time 0 and X at time 0, right? I will be able to find all the values of B, correct? Because F is a function of position and a function of velocity, and velocity is velocity. So that's called the initial value problem. Your job to do idealization, construct the equations of motion, put them in a matrix format, and then solve the equations of motion. That's what people do. Now, solving the equations of motion, we have two ways, either through the initial value problem or the boundary value problem. The initial value problem is I will give you initial conditions, you do iterations, and you get another iteration, and then another iteration, and you get the points as the trajectory is moving, point by point, right? So if I said to you, we're going to start with this, AX equals B, I know A, because A is the mass matrix, correct? I know the lengths, I know where the masses are, I know the masses themselves. B, if you give me x of 0 and v of 0, I know the initial condition. And then I can solve for x dot and v dot, the velocity and acceleration. So that's called initial value problem. And if you are given x0 and v0, so I have this x of 0 here, that's v of 0, those are given, right? I can fill a at time 0. I will have that because that's constant, right? Its length and masses, that's going to be the same. B at time 0 is going to take these values, substitute here, you will get B at time 0, right? So I filled this part, I filled that part. Now all I need to do is to find the inverse of A, right? Remember I told you that AX equals, that's if AX equals B, the way to solve this, multiplied each side with inverse. So that's going to be X equals A inverse B. And that's what I did. A inverse multiplied by B, that's a multiplication symbol. This is going to give you the unknowns, which are x dot and v dot at time 0, which is the velocity and acceleration. And then the next step will be is to multiply it with delta t. And the reason why I'm doing this is that if you recall, what is the derivative? So if I told you x dot, it's delta x over delta t, correct? Change of x, change of t. That's x2 minus x1 over delta t, right? If I would like to find the x2, what do? You multiply the derivative, that's the derivative, with delta t, and you add to it the initial value from here. And then that's going to give you the next iteration of the x or v, and that's how you solve for it. So give me the initial conditions. I will fill A and fill B. Find the inverse of A. Multiply it with B. Then multiply the derivatives with delta t, and add the initial value initial conditions. You will get the next iteration. So if I start with x of 0, that's position at time 0. Here I'm getting x at time the next iteration. And if it's velocity at time 0, here I'm getting the velocity at the next iteration. And then you feed it up to the next time, and you just keep doing this loop over and over and over and over again until you get your solution. Remember the example that we have 3 angles? That's theta 1, theta 2, theta 3, right? So this x actually is a vector, theta 1, theta 2, theta 3. So if I'm telling you this is x of 0, that's theta 1 at time 0, theta 2 at time 0, and theta 3 at time 0. So it's a vector format and matrix format, so that we can utilize MATLAB to solve all of them quickly without the need to do all the iterations. That is the initial value problem. That's how you solve it. And I wanted to make sure that we talk about this before we move on. If I want to show it to you schematically, we have the mass matrix multiplied by the v dot. The mass times acceleration equals force. We agreed that the generalized mass matrix is a function of position, which is the L's and the Z's, and the M's are constant. The force is a function of position and velocity. So look at this. If this is our example, see, the initial value problem, I will give you x of 0, which is theta 1, theta 2, theta 3 at time 0. That's position. And I'm giving you the velocity at time 0, theta 1 dot, theta 2 dot, and theta 3 dot. So in the initial value problem, I'm giving you, see this red line? It represents the position, which is the angles. Remember this angle here and that angle, right? These angles, right? And then you have the velocity. This is v1, v2, v3 for the masses. We're looking at the masses because the mass is the one that is moving. Segments are weightless, but we're looking at the masses. So if I give you the x and v, that's the initial condition, right? This is in the configuration space. That's where the position is, and that's a vector where v is. This is what we are getting. And then I'm telling you, do the iterations one by one. Then you will find the next point, the next point, the next point, and the next point. And each point will have a velocity, right? Correct? Because that's the next iteration, how much position and velocity. And then you feed it, and then you keep doing that thing until you end up with a final velocity here and the trajectory. So the x and the final velocity. Now, for the 2-point value problem, we're not going to do the iterations here, but what we will have is the initial condition, x0, and the final position, initial configuration, final configuration, xt, and the time. So I'm going to tell you, I want you to move from this position to that position in 0.1 seconds, right? And when you solve it, the output, this is initial, final, the output will be the trajectory and the initial velocity and final velocity. That's the difference between the two of them. We like to work with this, with the boundary value problem, because it's going to help us assess the muscle activity. That if you have initial configuration and final configuration, and we call this 2-point ballistic boundary value problem. Why ballistic? Because see the velocities, the sudden change in velocity. It's just like something is hitting on it, on the object. So if you have initial configuration, this is a configuration space, right? So this is theta 1, theta 2, theta 3. So that's configuration space. So this is, let's say, a standing position, and that's another position after some time. You can break it down into multiple phases instead of big phase. And the reason why this is the beauty about the boundary value problem. If you try to solve iteratively and we diverge, which means that we could not find an exact solution. So instead of going to from this point to that point, the solution went up, right? So somewhere else. That's divergence. So what do? You just break to smaller phases, and you solve 2 successive smaller phases independently. That's really a good tool or a good property of the boundary value problem. Now, if you do this, you solve each 2 successive phases independently, right? And if you solve initial x0 and x1, you will get the trajectory, initial velocity, and final velocity. Forget about this. And then solve x1 and x2. You will get another trajectory and another set of initial velocity and final velocity. Forget those. And solve the other one. So each 2 will be solved independently, right? And when you finish at the end, you will end up with at the discontinuity point where you have 2 velocities. The resultant of these 2 velocities is something that the muscles should adjust for, and that's how we find the muscle activity. How do we assess muscle activity from this approach? So a sudden change in velocity, a green and red, each one of them in a different direction. So there is a sudden change in that velocity at this point of time. So a sudden change in velocity implies a sudden change of momentum. And momentum is mass times velocity, right? Is that, yeah? And if we have a sudden change of momentum, can only result from an impulsive force. So the muscles need to act to create this. And the muscle provides the hammer blow, the target, to do this. And this is the first time that we can find new trajectories, and at specific time points, we can assess muscle activity, how much force the muscles are producing, non-invasively. And that's the beauty about the boundary value problem. right? So just keep in mind, the initial value problem, if it diverges, there are no solution, it's complicated. But the boundary value problem, if you don't have a solution, you either break it to smaller phases or you add more segments. So you have two options with the boundary value problem. You add more segments or you add more phases. This is the working model that we were talking about. And what happened is that we have 1, 2, 3 segments. We have 1, 2, 3, 4 mass points. And in this model, we were looking at some parameters like, see this SL, this is step length, and the alpha is the toe of angle. So each one of us, when we walk, actually, each one of us will select a specific step length depending on how fast you're moving, and also we have a specific toe of angle. Now, these selections are based on energy consumption. So your body is optimizing the energy consumption to minimize it. So, and that's how it selects these two. Okay, now we have three coupled pendulum systems, so 3 segments, and we have a swing and double support phase. The swing phase is that when the leg is in the air, and the double support when you have both legs touching the ground. So that's how we looked at it. And muscle activity only initiated at the end of the initial and the end of the configuration, and that's the beauty of walking. Your muscle does not have to be active in the swing phase. They are not actually. So when you walk, you should not be consuming energy or muscle. They intervene only when you're hitting the ground, and when you're leaving the toe off and the double support. Yes, and then the swing phase is the gravity is taking control when we do that. Okay, we have 3 dynamic variables that we were looking for. What do you mean by 3 dynamics? They're changing with time, right? The dynamic variables. And that's 3 dynamic variables, which is theta 1, let's look at this, theta 1, theta 2, theta 3. Those are 3 dynamic variables. But you can extract from them indirectly other variables that the healthcare providers interested in, like the toe of angle and the step length, right? But the things that change with time that we want to track are the angles, right? And then we can say for independent gait parameters. Now, see those dynamic variables? Those are the things that we can solve for and track as engineers. But healthcare providers want something called gait parameters, walking. So I can translate those into step length, the toe of angle, that's the velocity, and FS, what I care about is the step length, toe of angle, and the speed in which the subject is moving. So you need to look at these. And I can't tell a subject that, oh, I'm looking at your theta 1, theta 2, theta 3, but you need to tell them about those things. Toe of angle, step length, and the velocity of walk, the walking velocity. Those dynamic variables, the theta, the thetas and theta dot and theta double dot, we understand what they are, but we need to translate it to gait parameters so that people can follow what we talk about. Okay, now this is a schematic of how we are looking at in the configuration space in 2D. Here's what I want to do. X of 0, that's initial configuration, correct? So that could be theta 1, theta 2, theta 3 of zeros, correct? Right? V of 0 is the theta 1 dot, theta 2 dot, theta 3 dot at time 0. Correct? Right? So this is theta 1 dot, theta 2 dot, and theta 3 dot. And then you put it 0, 0, and 0. So initial configuration, initial velocity, right? This is an output of the boundary value problem. And X of H, heel strike, this is toe off. So we are saying that this is your initial condition when you toe off, and H, heel strike. Can you do that? And see this line? That's how the thetas are changing, the trajectory, right? And then you have the velocity at toe at heel strike, and then you go from this to the other one, because our walk is cyclic, right? So you can go back and forth, keep doing the rotation. So that's how we solve it. If we did the boundary value problem, the boundary value problem will give us all the possible walks a subject will actually take. So I can walk this way, right? But I can also walk this way, right? So the x-axis is the step length. I can change my step length, but I can still walk, correct? The y-axis is the toe of angle. What's that angle? So I can go this way. So if I have this, the angle will be large, correct? If I have smaller step, the angle will be smaller. So the boundary value problem will give you the entire space of all the toe of angles and the step length. And we got a subject, a real subject, a human being, and we asked him to walk, and we looked at what is the step length and the toe of angle, and he selected this point. Now, we were curious. Why didn't he select other points to move with? Because this is all the possible spectrum. So we constructed all possible walks, consist of the structure and the parameter that we built. And that's the beauty of the boundary value problem. So if I build a model, constructed the equations of motion, let's say for a tennis player, right? I can find all the possible movement a tennis player can perform, but then we'll see why is he or she selecting that. So every point represents a 2-point boundary value problem walk. So each one of them is a walk, specific walk, here in the space. And the plus represent a walk chosen by a human being, a subject. Why is that? We need to see why is this the thing. So we looked at energy consumption. So this is here the energy loss. So the lower this means that we are losing less energy, which means that we are efficient. Does that make sense? And we found out that this plus point has the lowest energy consumption, right? For versus step length and versus toe of angle. So the subject selected the step length and the toe of angle that actually minimizes energy consumption. And that's why people actually do this. Now, here's what happened. Imagine someone experience a stroke. They are consuming so much energy, and they're tired because they are not using the optimized, not optimizing energy. They lost control, and that's why people feel. Let's say if you give someone an artificial limb or some assistive technology, it's really hard because they're consuming a lot of energy, and that's why something we need to be careful about when we design our assistive technology solutions for them. And then we need to train them. So see the spectrum, the entire spectrum. The walk that the subject was used to have is not the best one anymore if they are injured or if they have experienced a stroke. So that's something we need to find out, where did they go, and then look at the energy consumption and then find ways for them to adapt. And that is the beauty of our work, is that we can actually help develop therapy approaches and therapy models based on data. So we can have the entire spectrum, and I will tell you this is where the subject is moving, and that's how much energy they're consuming. That's not good. We need to find another approach to teach them and train them to move in a different way. Does that make sense? Okay. Now, our model was very close. So see the top, this is the 2-point boundary value problem solution for the parameters, the thetas and the toe of angles. So the theta L is the left and theta R is the theta in the right leg. And those sigmas are also other parameters that we can find. But it's really close to the normal subject. See how close it is to the... So the model was actually representing a move, was getting us the right movement for the subject. Now, if you have no solution, as I told you, 2-point boundary value problem, I need to move from this point to that point. if my solution diverges, it's not going to that point where it should be. As a trajectory, you can always add segments, add multiple phases, 2-point boundary value phases. Now, at the discontinuity, when we have the two velocities, the discontinuity in angular velocity, so there's something, they're not on the same line. So I have discontinuity. That is where muscle activity is at the boundary. So I can see these lines. I can find the angular velocities and the changes in them, and that can give me actually an indication. I can calculate how much force the muscles are actually producing to counter this change in angular velocity, and that's how your muscle is working. And you can do this for any movement. If you build the idealization, for example, see the tennis, that I built the model, I built the equations of motion, but I never solved the equations of motion yet. So that's what we have there. See all the equations in the middle, down, those all the equations of motion. It's built, but I didn't have the time to do the solution. So I never had the time to find the spectrum of all the possible movement. And that's in 2 dimensions. So that's a project that I need to work on using both initial value problem and the boundary value problem, and see what I want to see all that entire spectrum of movement, and then I find a subject, I do a couple of serves, and then I would like to see where they are, and then look at this. But that's a project that I need to finish. I did not finish. So I constructed the model, build the equations of motion, but I didn't have the time to solve the equations. If you do this, you can build another thing. You can take the step length, and you can take the toe-off angle and build the energy, all of them together in one graph, right? What you need to do, you need to go as high as possible. So this is mechanical efficiency, right? So if you're walking, healthy subject will be on one of these, on this hill. That's the optimal gait. If someone got injured or had a stroke, they will go to one of these valleys. Their energy consumption will go high, extremely high. So they're not going to be efficient in their energy, and they're not going to walk with the same step length and toe-off angle. So if you see someone with a stroke, they will be moving like this, right? So step length is off, toe-off angle is off, and even the 2D movement is off with them. So what we can do is that I can look at this, and I can tell you, if you are here, or you're here on this gate, I can find approaches to train you to move you from here to there. See these lines? Those are each one of them, each line is actually an approach to train someone to move. And you can build animations to show the subject. This is how I'm going to do this. That's what we did with the lady. We showed her, this is what we want you to do. Can you do this? Can you do the animation? And then so we can help healthcare providers develop therapy protocols for them. But remember, it's based on the step length, toe-off angle, and how much energy consumption is going on there with this. And each model will be different. So here we looked at step length and toe-off angle. For the tennis, that model, what is the important thing? We need to speak with exercise science people. I need to know so when they do the serve, is it the velocity of the racket? Is it the angle of how the hand is holding the racket? So what is the thing? Is it the angle of the whole entire range of motion? So that's where we need to collaborate with exercise science and help other coaches, right? So for this gait, step length and toe-off angle is not our idea. We had someone in the lab who was actually a coach, and he helped us to identify that these parameters, these gait parameters, are important. Remember, we dealt with the dynamic parameters, theta 1, theta 2, theta 3, and I can have them for all movement. Now, but which are the gait parameters or the tennis parameters in the sport that matters? And then we can do the correlation between them, right? So in the boundary value problem, I can solve for optimal solutions, and we learned that we can find the forces of the muscles. So the weakness of the forward and inverse dynamics, that I can find new motions and I can find the muscle activity, is solved by the boundary value problem. As long as you have it in the constructed equations of motion using the Lagrange energy-based approach, because that's energy, right? That's what we're looking for. So to summarize the whole thing, the number of joints and body segment handled by a model is arbitrary. You're the one who's going to build the idealization of the model. Do we agree? Step 1. As long as the branches pattern is consistent with the acyclic directed graph, which means that you don't have closed paths. We should not have any closed paths with them. A complete movement solution is obtained. So we build the model. You create the equations of motion, then you do solution. So a complete movement solution is obtained by piecing together an arbitrary number of connected phases, initial configuration, final configuration. You solve each two separately, and then you move to the next two, and you will have this discontinuity of the velocity. Each ballistic phase is solved as independent 2-point boundary value problem separately, and the net impulsive muscle joint forces are model output. So I can find the new motions and net muscle joint forces in the interfaces. When we have two velocities, discontinuity. Muscles need to interact to make sure that this is smooth. And that's where the muscle is. And the model output of each motion solution include a mechanical energy efficiency and stability index. Now, the output of the model, remember, it's potential and kinetic energy. So I can know how much energy is consumed. And the stability index, do you remember the matrices? Do you remember something called the eigenvalues and eigenvectors? Yeah, I know. I know that look. But these eigenvalues and eigenvectors are stability index. So if you have the eigenvalue, you can, in the first one means that it's in x direction. I can say that this is, if that value is high or low, it can tell you if this movement is stable or unstable. So remember, engineering is an applied math, applied science. So these eigenvalues and eigenvectors, yes, they're numbers, but they have a representation in instability. They're stability indices, and if you can get them out, you can tell the healthcare provider and the patient, this movement is not stable in that direction. You need to change that motion. Right. So why are we doing this? I want you to know that part of rehabilitation engineering is doing this modeling. This is separate from building assistive technology and equipment and gadgets like wheelchairs or robotics. This is an important part that actually few people are working on it. And that's why you need to know that we have two tracks, modeling and simulation, and then you have the design development in assistive technology, in rehabilitation engineering. And that's why we spend this is going to be the last time we'll talk about it, but 2 weeks and a half is enough to talk about this and make sure that you know what this field is. Keep in 3 steps: idealization, constructing the equations of motion, solving the equations of motion. That is the entire field. And you can build whatever model you want, whatever motion you're looking for, and nobody built anything. The only model that we have is just the walk, the one that we built in New Jersey. That's it. So I'm trying to build that, but I don't have the time. But I'll be done with it, hopefully. And we have a tennis team, right? Yeah. So we can collaborate with them after we build the model and solve the equations of motion, and get some parameters. Tell them which one you're interested in after finding all my dynamic parameters. So I wanted to make sure that this is part of our understanding of what's rehabilitation engineering. Does it make sense with us? Idealization, segments, mass points, relation matrix, and then you have constructed the equations of motion, Newton, Lagrange. You solve initial value problem, boundary value problem, and these should be good. And that's an applied math approach.